All right, 4.18. For the casting shown, I don't know what a casting is, but for whatever the figure is, determine the largest couple M. So when they say couple M, they probably mean pure bending that can be applied without exceeding either of the following allowable stresses. So a tensile stress because it's positive, and a compression stress because it's negative. All right, so I think if they mean pure bending, what I would do is I would say, hey, let me see sigma is going to be equal to the negative of the moment times our y coordinate divided by I about the z, sorry, what am I doing? About the z-axis, this is not good. Let's do it on the white. All right, so we can use this formula and say that the sigma about the x-axis is equal to the negative of the moment about what axis? The moment about the z-axis times y divided by, why is it coming so bad? Sorry. I really want you to see this written well. And then divided by the moment about, the moment of inertia about the z-axis, okay? So I hope we're all on the same page. Now, they're giving us the couple, so there's no need to do any internal cuts. We need to solve for mz, right? So we need to find y, and we need to find iz. We do have the sigma, so that's a good start, right? So let's just look at the cross section. And just for reference, I like to put an x here and a y here. And now keep in mind that the z is going to go into the page using the right-hand rule because you'd curl your fingers this way. And that's what I made a mistake of in an earlier video. So now how do we relate that to the cross-section? Well, the cross-section is basically, if you were to see it in perspective, it would be this part right here of the beam, right? So you'd have, I hope that this clarifies a little bit, so it'd be right here. And so, well, if that's the case, then my x is going to come out at me. My x is going to come out at me. My y is still going to be up. My z is going to go this way. Well, obviously, this is not the final z, so I'll just call it a datum. I hope that's the right pronunciation. I keep changing because I don't know which one's right. So right here, from which we're going to calculate some distances. So let's see. We can leverage symmetry. We can say that we only want to find the y, and that's really all we care about because we want to find the distance eventually from the z-axis. Oh, the distance from the z-axis. So the bending happens, yeah, I'm correct. So the bending will happen about this axis, and this axis is going to be the z-axis. That's going to be my y, and my x is going to be coming out here. Well, the right-hand rule, some positives and negative will change. But yeah, I really don't want to give wrong information, so I always think twice, and sometimes I overthink. All right. So how are we going to do this? We want to find our y. Well, our y for the centroid. Well, there's a way to do this, and that is let's break these up, and then let's find the location of the centroids. We know they're there, so because we can leverage the symmetry of the specific shape, the sub-shape that we divided the cross-section into. So for the first one, we're going to have the area of the first one, so that's going to be 5 times 0.5, that's 2.5 inches squared, and we're going to put the y coordinate with respect to our datum. So that's going to be 0.5 plus another 3 plus another 0.25. So that's going to be 3.5, and I'm just going to write it down because I'm probably going to mess it up. 3.5 inches plus another 0.25 inches, right? And we're going to do the same for the second shape and the third shape. So say this is one, this is the second shape, and this is our, that's the same shape, and this is our third shape, all right? So we're going to have that for the first one. The second one is going to be have an area of 0.5 times 3, which is 1.5 inches squared, multiplied by wherever the centroid is compared to our datum. So that's going to be at 1.5 and another 0.5. So that's going to be at 2.0 inches. We're going to add the third shape. So the third shape is going to be what? Well, the third shape is going to be 2 times 0.5. So that's going to be a 1 inch squared. And we're going to multiply it by the y location of our centroid for that specific shape, which is 0.25 inches. Now we're going to add all the areas together. So that's going to be a 2.5 inches squared plus a 1.5 inches squared plus a 1 inch squared right there. Now let's throw this into the calculator and let's see what value we get, and then let's see if we made a mistake or not. So 2.5 times 3.5 plus 0.25 plus 1.5 times 2 plus 1 times 0.25, 2.5 plus 1.5 plus 1. Let me just check that I put everything in correctly. So 2.5 times 3.5 plus 0.25 plus 1.5 times 2 plus 1. I really hope I didn't make a mistake. Times 0.25 divided by 2.5 plus 1.5 plus 1. I should probably slow down. This is not helping. All right, 2.53. See how I'm slowing down? All right, inches. Let's see if that makes sense. So we know it's going to be closer to this one. So it's got to be 2 and another 0.25. And so it kind of makes sense that it's right here. I don't know if it's the exact number, but it is a number. So hopefully that's correct. Now we're going to find the I value. So for the I value, we can find the I for the shape 1. And what is the I for the shape 1? Well, it's going to be 112 from the centroid times the base, which is 5 inches, times the height, which is 0.5 inches to the third, plus the shift. Well, the area is 2.5. We already went over that. And now the shift, well, if we said that our z-axis is somewhere here, this is our z-axis, then we're going to have to find this distance right here. So let me change color. So we're going to have to find this distance. And so what is that distance? Well, we're going to take from the bottom, from the datum, it's going to be 0.5 plus 3 plus another 0.25. I'm just going to write it down. So times 0.5 plus 3, well, I can do that in my head. That's at 3.5 inches plus another 0.25 inches. I could have done that in my head. And then what are we going to do? We're going to subtract what? Subtract the height of the first of the shape 3. So that's 0.5 inches. And also subtract, actually no, because y of the centroid is from the datum. So we just subtract 2.53. That makes our life a little bit easier. So we subtracted 2.53. Let me just check that I'm doing my math right. So we want to get to 3.75. That makes sense. And I want to subtract my y. And then I want this squared. Now let's do the same for the second shape. So that's going to be 112 from the centroid. The base is going to be 0.5 inches. The height is going to be 3 inches cubed plus total area 1.5 inches squared. And we're going to multiply that by, now we want to find a different distance. Now we want to kind of find this small distance right here. So how are we going to do that? Well, that's going to be z. So the y location of the z-axis, which is 2.53 inches, minus the location of the centroid of the shape 2, which is going to, from the datum. So that's going to be 2. And look, we have it over here. It's nice. I should have done that earlier. 2. Right here. We close that, and now what? And now we want to square it, because that's the parallel axis theorem, which I don't remember the proof, but I like the proof. Now we do the same thing for the third shape. So the base is 2 inches, 2 inches right here. The height is 0.5 inches cubed, plus the overall area is 1 inch squared. And we're going to do what now? Well, we're going to find this distance right here. So we're going to have to do our y, 2.53 inches, minus 0.25 inches. Look, we have it right here. And all of that is squared. All right, so now that we do that, let's plug it into the calculator. Let's see what we get. And hopefully we didn't make a careless mistake. So times 5 times 0.5 to the third plus 2.5 times 3.5 plus 0.25 minus 2.53, all of that squared. And then we get 3.77. So 3.77 inches to the fourth. That's a small number. It makes me sus a little bit, but I guess we have decimals everywhere. Okay, so let's do that again for the second moment of inertia. So that's 1 over 12 times 0.5 times 3 to the third plus 1.5 times 2.53 minus 2 squared, and that's going to be 1.546 inches to the fourth. One more, 0.5 to the third plus 1 times 2.53 minus 0.25. So we get 1 over 12 times 2 times 0.5 to the third plus 1 times 2.53 minus 0.25. All that is squared. We get 5.22 inches to the fourth. So now we can find our total just as before. What's our total? It's going to be I1 plus I2 plus I3. And so that's going to be 3.77 inches to the fourth plus, I don't know why I put parentheses around everything, plus 1.546 inches to the fourth plus 5.22 inches to the fourth. So what is that? Well, let me just plug it into my calculator. So it's going to be 5.22 plus 1.546. I don't want to put the plus twice. Plus 3.77. And I get 10.54. 10.54 inches to the fourth. So this is the moment of truth, right? Well, kind of. We know at the top, where are we going to get tension and where are we going to get compression? Well, we're going to get compression at the top. So S at the top for the maximum. So the maximum distance away from our x-axis should be 6 KSI of stress. And so basically we can say that 6 top max should be equal to minus the moment about the z-axis times y distance divided by iz. Well, we have iz. What's the y distance for the top? Well, that entails finding this distance. And that distance is going to be what? Well, it's going to be the overall height minus the height of the centroid of the composite shape. So we can write, well, we can solve for mz. So mz is going to be equal to sigma top times iz over y, mz. And so we got our values, 6 ksi, 6 ksi times, and I like to put into base units, or at least, yeah, I'll just put it in base units. 6,000 pounds per inch squared. And then we multiply that by our I total, which is 10.54 inches to the fourth, right there. We want to divide by our distance y from the top. This is the only thing where we have to think a little bit. 3 plus another 0.5 and 0.5, that's 4. 4 minus y, 4 inches minus our y of the centroid, 2.53 inches. And so that's going to give us an answer. Now, are we top or bottom? We're at the top. Okay. Now for the bottom, we do sigma bottom times iz divided by y. But now our y is going to be different. Our y is just going to be minus 2.53 inches. This is going to be 600 pounds over inches squared. And here we're going to get, I made a mistake. I'll fix that. The bottom is going to be in compression. The compression at the bottom is going to be minus 15 max. 0.000 pounds per inch squared times 10.54 inches to the fourth. All right. So now we're going to do 6000 multiplied by 10.54 divided by 4 minus 2.53, and I get 4,302. 430. No. I get 4 point, I'm just leaving it in scientific notation. 30 times 10 to the fourth. The units are pounds per pounds times inch, and it's in the positive direction. Now, this is another issue, is where is our positive direction? Well, we know that our positive direction is going to be like this from our reference system. And then for the bottom, so I really hope I'm not making a careless mistake there. From the bottom, we're going to get negative 2.49 or 0.50 times 10 to the fourth pounds times inches. And so this is the one with the smaller magnitude, so this should be the answer for both, because we want the one with the smaller magnitude. However, and it's both in the same direction. So, however, I just want to make sure that sign thing doesn't confuse us. In this case, that moment is considered, I'll have to ask on this one, I'm not sure. What is the proper, or is the best, I guess, or recommended reference frame? So I'll ask that, or if you know, just put it in the comments. I hope this was useful, and I hope I got the right answer. I'll be checking that in a second, and I hope you have a good day. Bye.